Hello everybody, I'm Adam. In this problem, we're going to show that our points, given at A, B, C, and D, are the vertices of a parallelogram, and then we're going to find the area of that parallelogram. So we have our points A, B, C, and D plotted. So A with coordinates 0, 3, 2, B with coordinates 1, 5, 5, C with coordinates 6, 9, 5, and D with coordinates 5, 7, 2. Once we take a look at them in our xy plane, they look like they're kind of making a parallelogram, but we're not just going to use looks, we'll use math to find that. Okay? But first, let's kind of get an idea as, are all these points lying in the same plane? Means, could they be making a parallelogram to start with? So if we take a look at these z values of, namely points A and D, we see that they're both 2, and the z values of B and C, they're both 5. So they both have the same height in the z direction. So thinking in terms of a plane, we have our points A and D with the same height, and our points B and C with the same height. So in fact, they can lie in the same plane. So they could make a parallelogram. And it looks like it, and that's what we're going to confirm. So let's take a look at our points. And this is what I love about geometry, is being able to draw pictures. So we have this. Let's go ahead and connect our dots and give our figure some lines. So we'll go from A to B, B to C, C to D, and D to A. So remembering from geometry, what is the definition of a parallelogram? Well, it's a four-sided figure where opposite sides are parallel. So if we think of these segments of this figure as namely directed line segments, so each line segment can be thought of as a vector. So we'll think of the vector going from A to B, right? And the direction really doesn't matter. We could go from B to A or A to B. That part's not going to make a difference. But we'll just go in kind of a clockwise order. So from A to B will be a directed line segment vector. From B to C, think of that as a vector. C to D, think of that as a vector. And D to A will give us a vector. So once again, if we can show that the sides here are parallel, or the vectors there are parallel, that will mean the sides are parallel. And likewise, if the vectors on the top and bottom are parallel, that'll mean the sides are parallel, confirming we have a parallelogram. So that's how we'll start. So we'll start with our left and right sides. So we're going to show that our vector from A to B is, say, parallel to our vector from C to D. Okay? So before we do that, we have to find what the vectors are. So the vector from A to B in our component form, right, we're going to treat the point B like the terminal point. A is the initial point. So we do component-wise subtraction, where it's the components of B minus A. So for B, we have 1 minus 0, giving us 1, 5 minus 3, giving us 2, and 5 minus 2, giving us 3. Okay? So that's our vector AB, A to B. And finding the vector from C to D, well, same thing. D is our terminal point, C is our initial point. So taking the component, first component in D, 5 minus 6, gives us negative 1. 7 minus 9 gives us negative 2. And 2 minus 5 gives us negative 3. Right? So to show these are parallel, remember, two vectors are parallel if they can be written as scalar multiples of each other. So we take a look namely at CD. Notice we have the components 1, 2, and 3, but they're all negative. So this can be written as, say, negative 1 times the vector positive 1, 2, and 3. Or that's negative 1 times our vector from A to B. So the vector from C to D is a scalar multiple of the vector from A to B. So these two vectors are parallel. So we confirmed at least those two opposite sides are parallel. So now we do the same thing with our top and our bottom. So we're going to show that the vector from B to C and D to A are parallel. So we're going to show our vector from B to C is parallel to our vector from D to A. Okay, so same thing as before. We'll find the vectors in component form. So our vector from B to C C is our terminal point, B is our initial point. So subtracting, first component 6 minus 1 gives us 5. Second component 9 minus 5 gives us 4. And 5 minus 5 gives us 0. Okay, and our vector from D to A, same thing. A being the terminal point, D being the initial point. So 0 minus 5 gives us negative 5. 3 minus 7 gives us negative 4. And 2 minus 2 gives us 0. Okay? Which, if we take a look at this again, we see we have the same components, but we have negatives over here. So the vector from D to A can be written as, say, negative 1 times the vector of positive 5, positive 4, and 0, which is just negative 1 times our vector from B to C. So these are scalar multiples of each other. So these two vectors are parallel. Okay, so what have we just done? We've confirmed that the two sides here are parallel and the top and bottom sides are parallel. So then we have, let's put it over here. We'll write our answer. So our figure, given by the points A, B, C, D, is a parallelogram. Okay, so we've confirmed it's a parallelogram. Now we want to find the area of the parallelogram. And how do we do that? Well, if you remember, if we take the magnitude of the cross product between two vectors, say the magnitude of u cross v, this equals the area of a parallelogram if u and v are adjacent sides. Okay? So then all we have to do is, in our figure, take two adjacent sides, find the cross product, and then find the magnitude of that cross product. That gives us our area. So for adjacent sides, meaning sides that share a common point, we can take, say, the side from A to B and B to C. Again, you can take any sides that you want that are adjacent, but we'll take those. So first we're going to find the cross product. So we want a cross product of our vectors from A to B, cross with our vector from B to C. Okay? So finding the cross product between two vectors, we'll do this in our determinant form. So we take our determinant of our little 3 by 3 matrix, where the top row is our unit vectors I, j, and k, and then the next row is going to be the components of our vector A to B, which we have as positive 1, 2, and 3, and then the last row is our components of our vector from B to C, which we have as 5, 4, and 0. Okay? So what we have is we're going to leave ourselves a little bit of space. So the answer to this is going to be the linear combination of the unit vectors I, j, and k. So these are little blanks we're going to fill in with numbers. Okay, so the coefficient in front of I, right, how we find that is by breaking down this matrix into a smaller determinant. So we're going to cover up the column with I and look at this smaller 2 by 2 matrix and take the cross product and multiply each other. Not the cross product, but multiply by the diagonals and subtract each other. So 2 times 0 is 0 minus 4 times 3 gives us a negative 12. And for the next one with j, we cover up the j column and think of 1, 3, 5, and 0. Take the product down the diagonal. 1 times 0 is 0 minus 5 times 3 is a negative 15. And lastly, we're going to cover up our k column. So we have 1, 2, 5, and 4. Multiply down our diagonals. 1 times 4 is 4 minus 5 times 2. So 4 minus 10 gives us negative 6. So this vector, or cross product, is going to be negative 12i, two negatives, give us positive 15j, and minus 6k. Okay, so that's the cross product, and the last thing we have to do is find the magnitude of that, and that gives us our area. Okay, so our area, call it A, is equal to, right, our magnitude of our vector AB crossed with BC, right? And then the magnitude of a vector is just the sum or the square root of the sum of squares of its components. So the square root of the sum of squares of our components over here. So the square root of negative 12 squared plus 15 squared plus negative 6 squared. Okay? And so that's the square root of, let's take our calculator. So 12 squared plus 15 squared, sorry, negative 12 squared plus 15 squared plus negative 6 squared. So we get the square root of, say, 405. So we could leave it like that. We'll try and simplify it just a little bit. Noticing that 405 is divisible by 5. So 405 divided by 5 actually gives us, goes in 81 times. So this is equal to 81 times 5. And 81 being a perfect square, we can bring that out. So the square root of 405 can be written as 9 times the square root of 5. So that gives us our area. Thank you very much.